Welcome to The Explainer. Today, we're not just going to talk about database indexes like there's some abstract thing in a textbook. Nope, we're going deep. We're going to uncover the physical reality of how they work inside MySQL, right down to how your data is actually laid out on the disk.
So let's kick things off with a question that, let's be honest, every single one of us has asked at some point. Why is my database so slow? You think you've done everything right, you've added indexes, but queries are still crawling. Well, the answer often has nothing to do with adding more indexes, but with understanding the physical world your data lives in.
To really get it, we have to start at the very bottom, at the physical foundation. And I promise you, this isn't magic. It's all about order. And in the world of MySQL's InnoDB engine, that order starts with one single, absolutely critical concept, the clustered index. Okay, so let's break this down because it's a huge deal. A clustered index is not just some helper structure on the side. In InnoDB, it is the table. Your entire table's data is physically, literally organized and sorted on disk based on your primary key. The row data itself lives inside the leaf nodes of this giant index tree. You know, the best analogy for this is a dictionary versus the index in the back of a textbook. A dictionary is a clustered index. The words themselves, the actual data, are physically sorted alphabetically. You go right to the data. But a secondary index? That's like the book's index. It's just a list of keywords that points you to a page number. Two very different things. So, because your data is physically sorted by the primary key, your choice of that key becomes, without a doubt, the single most critical performance decision you will make. And this leads us to a fundamental battle: sequential keys versus random keys. Let's look at the two heavyweights here. On one side, you've got your classic sequential big int auto increment. Physically, this is a dream. Every new row just gets tacked on neatly to the end of the table. It's incredibly fast and efficient. On the other side, you've got a random UUID. Now, these are great for distributed systems, for sure, but physically, it's chaos. New rows are shoved into random locations all over the table. And that randomness comes with a really steep price. See, when a new UUID has to be inserted into a data page on disk that's already full, InnoDB has to do this painful operation called a page split. It literally has to break the page in two to make room. This happens constantly, leading to fragmentation, pages that are only half full, wasting tons of space, and it has a nasty side effect of making all your other indexes bigger and slower too.
Now, let's just talk about size for a second. A standard UUID, even if you're smart and stored in its binary format, is still going to take up 16 bytes.
And how does that compare to our good old big int primary key? Well, it's exactly half, just 8 bytes.
Now you might be thinking, come on, it's just 8 bytes, who cares? But here's the kicker, the part that has a massive ripple effect. Every single secondary index you create has to store a copy of that primary key. So if your key is twice as big, all of your other indexes are now also twice as big. That means slower writes, slower reads, and more memory usage across the board. It adds up fast.
Okay, so we've hammered home how vital the primary key is. But what about all those other indexes we're creating? Just because you can put an index on a column doesn't mean you should. And that brings us to the next big question you have to ask. What is the index's cardinality? Cardinality is really just a fancy way of saying how unique is the data in this column. High cardinality means lots of different values. Think something like a user ID, where every value is unique. Low cardinality means you've only got a few distinct values, like a status column that can only ever be pending, shipped, or delivered. And the difference is huge. An index on user ID is amazing. It's super selective. It can find one specific row out of a million instantly. But an index on status? If you search for all the shipped orders, you might get back 300,000 rows. The index barely helps the database narrow things down at all.
And that's exactly why this is so often called an anti-pattern. You have to remember, the database optimizer is smart. It'll look at an index with terrible selectivity and just ignore it. It'll decide it's actually faster to scan the whole table instead. So you're paying the cost to maintain that index on every write for literally zero benefit on your reads.
I mean, just look at a distribution like this. If your query is searching for a status of active, and that represents 60% of your entire table, it is way more efficient for the database to just read the table from start to finish. Using the index would mean jumping back and forth between the index and the table data hundreds of thousands of times. No way. So, let's recap. We want selective indexes, we want small primary keys, But what's the end game? If our goal is to make reads as physically fast as they can possibly be, then we need to talk about the holy grail of indexing, the covering index.
A covering index is just what it sounds like. It's a secondary index that is so perfectly designed for a specific query that it contains or covers every single column that query needs. The result? The database never even has to go look at the main table. It gets everything it needs from the index alone.
Let's look at the physical difference here. The normal process is 2 steps. First, MySQL looks in the secondary index, and then, for every match, it has to do a second lookup into the main table to get the rest of the data. With the covering index, it's just 1 step. MySQL finds the data in the index, and that's it. It's done. That second, very expensive step is completely gone.
And the performance benefits here are just staggering. You completely eliminate that extra lookup, which means you slash the amount of I/O your disk has to do. Your indexes are smaller, so they're way more likely to fit entirely into memory, and the result is that your queries can be an order of magnitude faster. Seriously, this is a total game changer for read-heavy applications.
But, and you knew there was a but coming, like everything else in engineering, there is no such thing as a free lunch. Every single index you add to your database, no matter how clever, comes with a cost. It is a fundamental trade-off.
And the trade-off is actually pretty simple to understand. Indexes make your reads, your select queries faster. That's the whole point. But they make your writes, your inserts, updates, and deletes slower, because now the database has to update the table and every single affected index. Plus, of course, they all take up space, both on disk and in memory.
So at the end of the day, your job isn't to chase some mythical perfect index that solves all your problems. It doesn't exist. Your job is to understand these physical realities, the cost of a random key, the value of high cardinality, the incredible power of a covering index, and design the right compromise. The real question isn't what's the perfect index, it's what's the perfect compromise for my specific workload.